The Heisenberg Uncertainty Principle is one of the most foundational and weird parts of quantum mechanics. Basically, it says that you can never precisely measure both the position and momentum of a particle at the exact same time. Uncertainty principle is the fundamental relation between the measurements of position and momentum, and is expressed as follows. Where delta p is the uncertainty of momentum, delta x is the uncertainty of position, and h is the Planck's constant. This formula describes the limitations of measuring the properties of particles with complete accuracy simultaneously, which are position and momentum in this case. The product of the uncertainty of position and momentum is more or equal to a constant, and this constant is defined as the Planck constant h divided by 4 pi. In other words, this equation means that if you know where a particle is located more accurately, then you know its momentum less accurately, and vice versa. Measuring one property of the particle actually changes its value, making it impossible to ever know both at the same time with complete accuracy. To measure the position of an electron, we typically use light, since light displays wave-like and particle-like properties. These particles of light, also known as photons, have some energy associated with them. So when the photons hit the electron, they transfer some of this energy to the electron, effectively giving it a push. This interaction also increases the momentum of the electron, which in turn further disturbs its momentum. In the context of the uncertainty principle, uncertainty cannot be zero, as it produces meaningless results. If the uncertainty in position, which is delta x, were to be zero, then the product of momentum and position would also be zero. However, any value of the uncertainty in the above product would result in infinite uncertainty in the other quantity or factor. Hence, anything divided by zero is infinite, or it is not defined. Therefore, the uncertainty principle inherently implies that the uncertainty in position and momentum cannot be zero simultaneously. The principle is a fundamental aspect of quantum mechanics and has been experimentally confirmed many times. The Planck constant is a fundamental constant used in quantum mechanics. It relates photon energy to its frequency through the Planck-Einstein relationship as E equals hf, where E is the energy of the photon and f is its frequency. Its value is 6.63 multiplied by 10 raised to power minus 34 joules second. The Planck constant quantifies the energy of a single photon, which is the smallest unit of energy that can be exchanged in a system. If the value of this constant had been different, the quantum world would also have been different. If the lower Planck constant would involve less uncertainty and fewer quantum effects, which would make the behavior of particles more classical. The other possibility, a higher Planck constant, would involve more uncertainty, which would make the quantum world more uncertain and